Okay, so now in this last video, let's apply what we have covered so far in theory, but let's take a look at a real-world example. And let's say we want to explain infant mortality by GDP per capita, inequality, and gender parity. And this is really more like a practitioner's guide on how to do a regression. And a good ordinary least square regression is supposed to be blue, which means it is the best linear and unbiased estimate. And so what you try to do is, in step one, you have to have a theory. What do you expect and why? So maybe you want to do a hypothesis table. So if we go back here and we say our dependent variable is GDP per capita. Our dependent variable is infant mortality. So let's abbreviate that inf more. And then our independent variables are, for example, GDP per capita, so then when we regress GDP per capita and infant mortality, I would expect a negative sign because richer countries have better health care, so they should care. The children are more likely to survive. About income inequality, if there is more inequality holding everything else constant, then I would argue that there's more poverty holding everything else constant. So I would think that inequality increases infant mortality, again holding everything else constant. What about gender parity? The more women are empowered, I think the better it is for the children, and greater gender parity should reduce infant mortality. So that would be like a snapshot of the theories. This is what I would expect. And that is what we do in step one. Then what we do is we check for normality and correct for non-linearity whenever possible. And that is necessary in order to make sure that our regression is actually linear. So that takes care of the L. And we have already seen, of course, that the OLS estimates, they are actually unbiased. But checking for normality and to correct for nonlinearity also controls for having the best estimate, and the best estimate is the one that has the least variance. But yeah, I think it becomes clearer once we see some of the problems that we can run into. So then step three, we generate a correlation matrix and check for multicollinearity, which may help diagnostics when coefficients lose their significance or change signs. Because sometimes things move in the same direction. For example, countries that are richer, that have a higher GDP per capita, they are also often countries where you have greater income equality, and very often you also have more gender equality. So we want to check for possible problems related to what we call multicollinearity, which is the problem that the same variable, they correlate highly on the right-hand side and they are not truly independent. Well, then in step four, we run the regression and check whether the coefficients are in line with theory. And the last step is that we check the residuals for normality, and we want to make sure that there's nothing that looks predictable or that can be detected in the residuals. And of course, what I'm showing you here is a very simple cross-sectional regression. And of course, there's so much more you can do. There is panel data analysis and time series analysis. But this is just an introduction into regression analysis. Okay, so here we see our indicators that I want to use. So, and what I do is I collect data from the World Bank Development Indicators database and all other averages between 2016 and 2025. So I have to average that out, and then I got a sample size of 124. Okay, so let's replicate this one again. So our variables are the mortality rate infant per 1,000 live birth, GDP per capita in constant 2021 international dollars, and then we have school enrollment, primary and secondary. Okay, so let's go to the World Bank Development Indicators database. So if you just Google for WDI, one of the first hits is already the WDI. And so then we go, you see we can select here our countries, and we have here all, but that includes things like the European Union or East Asia and the Pacific, or regions like Sub-Saharan Africa. We want to limit it to only countries. So now we have 217 countries, and we select them all. Okay, so now we go to the series, and you can see the WDI has a total of 1,486 series. So yeah, so we need to find GDP per capita. So GDP, and you can search, so let's say GDP per capita. So now we search, and now we can click on GDP and narrow it down even more. And then I want GDP per capita, PPP, constant 2021 international dollars. Okay, so then we had infant mortality. So I just search for infant. And then we have here mortality rate infant per 1,000 live birth. That's the other one. And you can see I have now selected two indicators, GDP per capita and the mortality rate. So next I want the gender parity index. So let's see what we get when we search for gender. So it says we wanted school enrollment, primary and secondary. This one, school enrollment, primary and secondary gross gender parity index, GPI. In the last index we wanted was the Gini coefficient. And we search this one, okay, Gini. So now we have selected for indicators, and then for the time frame, I think we set the last 10 years, 2016 to 2025. Okay, so now we have everything, and now we can apply the changes. And now we should actually see our data. So we have 217 countries, 4 series, and yeah, sometimes it takes a little bit longer. Okay, so now here it is. And so now we can download the data. So we go to the download options, and we download it. And what you want to do is you want to download it. You go to advanced options, and there is an option, and you want to download it as a list. Also download it as a table so that you can see the difference. But basically the difference is that whenever you download data as a list, you have not a separate column for each variable, but they are all listed. And if you download them as a table, then it's a little bit more difficult to work with them in Excel, especially when it comes to data wrangling or cleaning up a data set. Because when you download it as a table, we have all the countries and then underneath the variables, and in the columns the year. It's a little bit more difficult to navigate. So now I can download it to my computer, and so now let's see what we get under history. Okay, download. Hope it doesn't take too long. It's loading. Well, what I can tell you is that the WDI, it's really a very valuable resource, especially when you work with cross-sectional data. And normally, it really doesn't take that long to download the data. I feel whenever I record a lecture video, that's when it takes the longest, but you see now the data is there. So let's open it. And so this is what it looks like. Enable editing. And you see when you download it, maybe the first thing we want to do is fit to content. And then we have the country name, and you see we have GDP per capita, mortality rate, and it's all in a list. So what you want to do first is you want to first sort the data by the series code. And this way you don't have different series for each country. So the data set starts with Afghanistan and ends with Zimbabwe. And you can see we have already here 8,681 rows. Now from a data science perspective, this is still a small data set, but from a introduction to regression, it's a large data set. So the first thing we want to do is we want to sort the data, and we have to put them into column. But for each year, I want to have Afghanistan 2016, and then Afghanistan 2017, Afghanistan 2018. So what that is I basically want to stack time series for each unit of observation. And the way to do it is I sort the data by the series code. Okay, if we go to the metadata, we have the series code in the first column. The first thing I do is I sort here also by series code. Go to data, sort, and then sort by code A to Z. So the first one is GDP per capita. Okay, what I also want to do is I want to abbreviate those, because whenever you build a data set, you don't want to write GDP per capita PPP in parentheses constant. That's too long. So we have to abbreviate the data. And GDP per capita is lowercase y. The gender parity index, I don't know, I call it GPI. Gini index is just Gini. And the infant mortality rate, I call that inf mortality. Okay, so you see we have now sorted by code, and now I do the same thing in the data set that we downloaded in the data sheet. So we highlight everything, and then we go to data, sort, and now we sort by series code. And then we see now we have all the GDP per capita. You see So we have now the 10 observations for Afghanistan, then we have Albania, and it's all GDP per capita. Okay, so now if I go and I search for the next Afghanistan, I just search for AFG, you see now I'm at the school enrollment column. So what I do is I copy the entire series beginning with the first school enrollment, primary and secondary gender parity index for Afghanistan. I highlight everything and I cut it and paste it next to the first value that still says GDP per capita, but I note that the second column begins actually with the gender parity index. But I also copied now the data for Gini and infant mortality, but they are sorted. So that means as I copied the series next to column G, so column G is Y. So the second column is the gender parity index, and the third column is Gini, the fourth column will be infant mortality. So we have here Gini and here infant mortality. So actually I just go up here now. So this is our data, but now look, when we go to Y to the end, you see there is this overshoot because I did not only cut the gender parity index, but also Gini and infant mortality. So I just cut now that overshoot and I paste it again next to GPI, which is the Gini, and now I have one more overshoot, which is the infant mortality, and I cut this and put it again into its designated column. And now when I go to the last filled row of column J, where I have infant mortality, it needs to be equal with all the other ones. So that means I have sorted the data correctly. And now I can delete the overshoot, everything below the first time it says Zimbabwe, and the last Zimbabwe of that block of Zimbabwe observations. Okay, so now I can make it even nicer. So I don't need the series name anymore because I put them into columns, so I can delete that. I don't need the series code because I have already labeled my observations, and I don't need the time code. So now we have a nice data set. One thing you always want to do whenever you download data set, there is always still something maybe hidden at the very bottom that you overlook. So here at the very bottom we still have when I downloaded it. So you want to delete that too. One way you can do is you just delete everything below your last filled cell and everything to the right of your last filled cell to the right. And then we can fit to content. Okay, so final thing what you want to do for maybe data set aesthetics is maybe limit the decimals. There's really no point in showing too many decimals. And then again, fit to content. And maybe center everything. Okay, this data set is now a stacked time series or a panel. But what I want to do is I want to take the average for each unit of observation. So the units of observations are the countries. And you can see, For example, for Afghanistan, I don't have any Gini observations. So missing observations is a problem. But what I do now is I look for the group averages, and I just want to build a final data set which captures the group averages. And there is a super useful tool in Excel, which is the pivot table. So if you go to Home, it's actually Data. There is if you go to Insert, and there is something called Pivot Table. So under Table, Pivot Table, you want to insert a pivot table. So let's go Insert, Tables, Pivot Table. In case you don't find it, you just can search for Pivot Table. But it's Insert, Tables, Pivot Table. And then that's okay. And I want it as a new worksheet. Okay, so this is what it looks like. So now I want all the rows filled. The first row, I want to have the country name. So, and I dragged it into the rows. Okay. Then next, I want to have I put into values the count of Y. Then GPI, I put it underneath, and you see it creates columns and infant mortality. Okay, but what I don't want the count. What I want is the average of each observation. So I want for Afghanistan the average GDP, which is Y. So I can right click into this cell and I say Format Cells. And then I say you right click and you go to Value Field Settings and you say Average. You can also do it inside here, but it's a little bit more finicky. You go to Value Field Settings, Average. I find it easier here. Right click, Value Field Settings, Average. Last one, Count, Value Field Settings, Average. Okay, so that's it. So now you can see that we have a number of divide by 0, which is equivalent to there is no observation. So Excel tried to divide something by 0 and then returned an error term. So what I do next is I just copy and paste this data set, but maybe without a grand total, into a new sheet, and I clean it up there. So I copy it, and then I say right click, I just want the values, no formatting. Okay, now it says average off. We don't need that, so I want to remove everywhere the sentence or the part of the sentence average off, and I say search for average off and replace by nothing, replace with by nothing. Okay, so now that looks more, and I want to also remove again all those decimals. Right click, maybe 2 is enough. And where it says row labels, it's actually the country. Okay, so what do I do with those missing observations? I just want to have a data set for simplicity which only has complete observations. So what I create now is I want to find all the units of observations that have at least 1 divided by 0. So one trick in Excel, I create a column and I call that sort, because later I will sort by that column. And I calculate the average of those observations. GDP per capita, GPI, Gini, and infant mortality. Well, whenever one of those if Excel cannot calculate the average, then this is because there is a divide by 0. So now we get an error message. But Albania has complete observation, so I get a number. So now if I copy down that formula, I see whenever I have a divide by 0, I must have some missing observations. So now what I do is I'll just sort by the last column, which I call sort for that reason, and I say sort by the last column, which is sort, smallest to largest. And what Excel now did, it pushed all the diffs divided by 0 to the bottom. And here they are. And what I do now is I just delete them all, because I don't need them. They have missing observations, so I delete them. And now I maybe put the column headers, the labels in bold, and I sort again by alphabet. So I sort again the data, sort by country. Okay, so now we have a data set that we can work with. So let's see again, we have Y, GDP is actually lowercase y. We have infant mortality, GBI, Gini. Okay, so the first thing we do, so we have also 124 observations. Let's double check again quickly. So it starts at 2. Okay, so it should be the same data set. Good. And I don't need that column sort anymore. I can delete that. Okay, this is our final data set. So corresponding to those values. So now let's get started. The first thing we want to do is we want to have descriptive statistics. And you can see on the slide I have here the descriptive statistics like mean, standard error, median, mode, others, minimum, count. How do we get that? Well, in order to get that, we need to go to Excel and we go to data. Now we go to data analysis. And if you haven't downloaded data analysis yet, which I'm very sure you have, make sure you activate your Excel add-ins with data analysis. And you see there is something called descriptive statistics. Just say yes. Then we pull up, our data has labels in the first row. And I want the descriptive statistics for Y, GPI, Gini, infant mortality, and then you say yes, and I want to put it into a new worksheet ply, and I just want the summary statistics. And now we have a new sheet, and you see we have now GPI, Gini, infant mortality, Y, so the mean for all the observations of GDP per capita is, for example, 25,750, and that should be the same as here. So this is where you can get summary statistics. Should be very similar to what you see here. I'm saying should be very similar to what you see here because the World Bank sometimes updates data. So if it doesn't look exactly the same, it's probably because better data is available or more data is available. Okay, so now we can take a look at the statistics. Of course, we can interpret them. So for example, whenever we know that the mean is very far above the median, then our data is skewed to the right. But when you want to look into things like skewness, you typically want to see a histogram. So let's go back to our Excel sheet, and sheet 3 I call summary stats. Okay. It's not necessarily the nicest format in Excel. Other programs might be a little bit better. But once you understand the basics of regression, you probably don't work with Excel anymore anyhow, but you migrate to another program. Okay, so now we have to go back to sheet 2 and I call sheet 2 final data set. Okay, so now I want to take a look at the distribution of, for example, Y. So there is something that we can go to insert, recommended chart, and if you go to all charts, you see there is histogram. You can say OK, and this is the histogram of Y. Well, we don't have to save it, we already can just look into it, but we can see, oh, this data has really a long right tail. This data is clearly not normally distributed. So let's take a look at something else. What about GPI? Let's highlight everything, go to Insert, Recommended Chart, All Charts, then Histogram. Okay, that looks already a little bit better. It seems to have a healthy mean, and then it flattens out left and right. So it's not as skewed. Okay, let's take a look at the Gini coefficient. So insert, recommended chart, all charts, histogram. Yeah, a little bit skewed to the right, but to be honest, not that bad. So, and the final one is infant mortality. Let's highlight everything. And then recommended chart, all charts, histogram, also bad. It's highly skewed to the right. Okay, so why is that? So why is that a problem? So now we have seen all the scatter plots. You can see them again here. Infant mortality, heavily skewed GPI, and Gini. Well, this data is set, whenever data is skewed to the right, it is said to be nonlinear. And why is that a problem? Well, it is a problem when it comes to creating a scatter plot. So let's say I want to create a scatter plot of GDP per capita against infant mortality. So I highlight all my observations for GDP per capita, which in my case is column B. And I also highlight all the observations in column E, where I have infant mortality. Okay, so now I have highlighted the two columns, and now I want to show a scatter plot. And Excel always will take the first highlighted column of the data area and puts that on the x-axis. So in my case, I already have I on the x-axis where I want it, because Y is the independent variable. The dependent variable is typically on the y-axis. So now we go to Insert, Recommended Chart, and the first one is the scatter plot, and I'll say OK. So now let's take a look at this scatter plot. Well, this is not a good linear relationship, because if you carefully look at this data and we fit a straight line, which we can do by adding a trend line, the trend line is really bad, because at very low levels of income, let's say GDP, on the x-axis you see income. At very low levels of GDP, the trend line actually underestimates the true infant mortality burden. Because there are like so many countries that have so much higher infant mortality than what's being predicted. Well, then for the middle range of income, maybe from 20 to 60,000, the trend line all overestimates the true infant mortality. So there is not a single one between 20 where the trend line would make more or less an accurate prediction. And then it gets even worse for countries of that have more than 60,000 of income. Well, the trend line would predict that the infant mortality is negative, which is of course nonsensical. So this is not a good model. And the problem is non-linearity, and the non-linearity correlates or is a result of the fact that both infant mortality and GDP per capita is so skewed to the right. So a good trend line would actually be a curve that looks maybe something like this. That would be a good trend line. But that is not linear, because OLS is the best linear. And we have seen the linear one is really bad. Well, the reason why the scatter plot is so bad has to do with the fact that our data has values that get higher and higher on the right tail. So you can think of it like this. So we have observations, let's say 1, 2, 3, 4. And on the x-axis, the values get higher and higher. So let's say first, maybe we have a 1, then we have a 10, then we have 100, then we have 1,000. So that means the observations, they get pushed further and further to the right. So now the trick of converting this nonlinear data where the distance becomes bigger and bigger is to take the log. But before we take the log, let's first remember what is t raised to the, in this case, observation. Actually, it's not the observation. Okay. Well, what is t just raised to? Let's say here, what is t raised to the 0 equals t raised to the 0. Okay, that's 1. What is t raised to the 2? Well, that's 100. What is t raised to the 3 or cubed? Well, that's the 1,000. Oh, I forgot here. That should be 1. 1, and this is 2. And the last one is equals to 10 raised to the 3. It's 1,000. And if we still had 10,000, we could add another one. So now our 4 observations that are nonlinear, well, if we take now the log with base 10, log base 10, well, then we get equals log, so this is base 10, okay, 1, base 10, 0, and then you see we linearize the data. So by taking the log, what used to be 1, 10, 100, 1,000, and maybe 10,000, that becomes 0, 1, 2, 3. So the distance becomes equal between. And that is what we call to linearize the data. Okay, so now let's linearize the data. And I don't take, we can take log base 10, doesn't matter. So, okay, so now we create a new variable, and I call it log y. And then just for illustrative purposes, I quickly jump to log infant mortality. Log. So we create a new series where we take the log. Log inf mortality. Okay, this is log 10, and then here equals log of this base 10. And now we just copy down that formula. And now let's take a look at the distribution of the logged variables. So let's highlight the log of y and see what a histogram looks like. So let's go to recommended chart, all charts, histogram. And you see that looks already much healthier from a statistical perspective. It's not perfect, but much better. What about the log of infant mortality? Insert, recommended chart, all charts, histogram. Well, also the skewness is much better. Well, that's the best that we can do at this point. So now let's take a look at the scatter plot. So again, we highlight the columns of log y and log infant mortality. The log of y will be on the x-axis. Now let's take a look at the scatter plot. And you see this already looks much, much better. To see it, maybe we can limit the x-axis and say the minimum is actually 2.5, and then we add the trend line, and you can see this trend line has a much better fit. So this is now a good linear fit because the error terms, they are nicely and equally distributed around the trend line, and we don't have the same problem that we had earlier here. Okay, so now we have looked at the distribution of all the variables, and what we have seen is we definitely have to transform GDP per capita because we get this highly nonlinear relationship, and of course we need to transform infant mortality. When it comes to Gini, there was not so much we could do. So when it comes to doing the regression, we have to look at all the individual scatter plots and then make a decision what is best. So we played around with different logs, and at some point of time, when you look at data, you can also test for certain things like normality, does it get better or not? But yeah, so here I would suggest that we definitely take the log of y and the log of GPI and the log of Gini. So we transform everything. But when we transform the data, there is one important thing to keep in mind, and that is whenever you have a regression and you move from a regular regression to a so-called double log regression, then the dependent variable becomes, the coefficient becomes an elasticity. So let me quickly illustrate that again, step by step, what you also see here. So let me create a new slide. Okay. So if you have a simple regression like, let's say you have infant mortality is some intercept plus a certain coefficient, let's say 0.3 times GDP per capita. Let's just assume that's the case. And actually, to make more sense, let's assume the coefficient is negative. Okay, so this is what we estimate, so let's put ahead. So nothing is transformed. What that means is that how we have to interpret that is a $1 increase in GDP per capita decreases infant mortality by 0.3. And this was per 1,000 live birth, so by 1.3 per 1,000 live birth. Okay, things become different when we work with double log regression. So when we have the log of infant mortality as the dependent variable, and we regress it on beta 0, and let's say our coefficient this time is 0.02 times y, then the 0.02 is an elasticity. Okay, so again, this is beta 1. Once beta 1 is negative 0.3, if I don't take a log on both sides. And here, actually, it's a double log regression. I have to the right the log of y. So now, okay, if we take the derivative with respect to y, then we can say, well, the first derivative of infant mortality with respect to y equals negative 0.3. And then we would say, okay, a $1 increase in GDP per capita reduces infant mortality by 0.3. But now what about here? So now we have here d, the log of infant mortality, and we take the derivative with respect to ln(y), and that is negative 0.02. Okay, but now what that means is that a 1 unit increase in y increases the log of infant, or decreases the log of infant mortality by 0.02. And what does that mean? Well, in order to see what that means, we need to realize that whenever we take a look at the regression, whenever we look at a log transformation, let's say here on the x-axis I have infant mortality. And on the y-axis I have the log of infant mortality. Well, then this relationship, whenever you take the log of something, it starts looking like this. And you can see that at every point, the slope becomes flatter and flatter. So it turns out that taking the derivative of the log of infant mortality with respect to infant mortality, that is equal to 1 over infant mortality. Okay, it's just like the log of x derived with respect to x is 1 over x. And now x is just the log of infant mortality. Well, rearranging this term just suggests that, the log dln infant mortality can be written as d ln infant mortality over, so this just goes up here, infant mortality. Well, and this term is nothing else but the percentage change of infant mortality. So that means that, this means that it's a percentage change. So instead of writing DL and infant mortality, we can also write this term as the percentage change of infant mortality. Okay. And likewise, the log of y, when we say the change of log of infant mortality with respect to the change of ln y, well, that is also the percentage change, but this time of GDP per capita. So the denominator is the percentage change of y. So that means our coefficient is 0.02. So, okay, so what does that mean? So that means if, for example, a country has a GDP per capita today, let's say, so today, let's say GDP per capita value is 100. And infant mortality is, let's say, 50. Okay. So then, if tomorrow the value changes from 100 to 110, well, that is equivalent to a plus 10% increase, or 0.1. Well, then it follows that GDP should go, infant mortality will go down by 0.1 times negative 0.02, which is 0.002%. So that would be 0.002, or it will go down by 0.2%, right? So that would be the interpretation, right? So that's why, you got to be careful whenever you run a double log regression, the interpretation changes. Okay, so now let's actually run the regression. And what we still need to do is we need to finalize all the other transformations. So let me go back to our Excel sheet. Okay, so we have log of y and I delete it here, and then I just say here this is the log of GPI. Let me quickly see in the regression. I think I have taken the natural log, which we can also do. So in order to get the same results here, I actually took the natural log. There is really no difference. You can take either one. I guess most people prefer the natural log because it seems somewhat more natural. So let's just replace it by the natural log, ln y, ln GPI ln Gini and ln infant mortality. So this is ln, not log, ln of y. Okay, I just can copy this to the right, and I can copy it down, and I just remove some of those decimal points. Okay, so now we have everything in terms of natural logs, and now we can run the regression and interpret the regression results. So let's do the canonical approach, and let's just throw in everything at once, and let's hope that this is already giving us good results. So we go now to data analysis, and then you see there is something called regression. Okay, and then it wants to know the input y range. So the input y range is our dependent variable. So we click into it and we highlight the log of infant mortality. Then the input range, that is everything from ln y, ln GPI, ln Gini, and we can highlight them. So now our data has labels, which are the column headers, and we can also click on residuals, and actually then let's do it later. So let's just take a look at the regression output, and we want it in a new worksheet ply. Okay, so now this is our regression results, and you see again an R squared. Let me just delete some of those decimal points here. You see again the ANOVA table, so we know what the R squared is. We know the ANOVA table, we talked about that. And here you see the coefficients, that is of course the most important part. So the most important thing when you run a regression, you check with your hypotheses and whether something is significant. So first of all, GDP per capita, the log, is negative 0.79, and the p-value is very, very low. That means it is clearly significant at, I don't know, something even probably at 0.1% or so. So because the p-value is clearly less than 5%, this is highly significant. And what that means is that a 1% increase in GDP per capita reduces infant mortality by 0.79%. So that is how we would interpret it. The gender parity index was actually only significant at 10%. So the p-value is 7%. So that means it is not significant at 5%, but it would be, no, it's still relatively strongly significant, especially for data like this. It would be a bad p-value maybe for medical tests when really lives are at stake. But if you want to get some relationships for policy, it is significant at 7%. And of course, nobody would disagree that having better gender equality would not be good for the well-being of the children. So it has the right sign, just like GDP per capita, it also has the right sign, and it is still relatively strongly significant. Maybe, yeah, it's significant at least at 10%. The Gini coefficient again is also highly significant, and the more inequality we have, the greater is infant mortality. So a 1% increase in the Gini coefficient will increase infant mortality by 0.85. 0.5%. So all the signs are correct, and they are relatively strongly significant. And of course, this is just the entry into regression analysis, and there are many other things that you still need to do. So let's interpret next the regression results. So here on this slide, you can see again how we ran the regression. And so here are the regression results. So it's again 0.79, 1.2, so the same values, so we don't have to spend more time on this. Again, interpretation of the regression results. So a 1% increase in GDP per capita decreases infant mortality by, on average, 0.79%, and it is significant at a p-value of less than 1%. And a 1% increase in the gender parity index reduces infant mortality by, on average, 1.24%, and it is only significant at 10%, less than 10%. And a 1% increase in income inequality increases infant mortality by, on average, 0.85%, and it's also highly significant. So all models carry the expected sign, and the model in its entirety is also highly significant, which of course is always the case whenever your variables are individually already significant. Then the f-statistic is also, the f-test is also significant. Okay, so there's still a residual plot that we can look at the residuals. And how did we get? It looks pretty normal, so that's a good sign. If that were also skewed, that would be a bad sign. That would be an indicator that we may have omitted some variables. But yeah, they look pretty healthy. So how did we get that residual plot? So let's go back to our data set and let's rerun again the regression. Regression, okay. But let's also store the residuals. And here there's even a residual plot. And let's click on it. Actually, we didn't need that residual plot. That is for each individual variable, but we don't need that. So somewhere, oh, here's the residuals. So here's the residual output, and what I did is, what we examine is the residuals for our 124 observations. And if we go to the residual plot, then insert recommended chart, all histogram. So this is the residual plot that you see in the slides. And what I did is I just reduced again some of the decimals here. So you can see it's very normal. So overall, our model looks pretty good. Okay, so these are the steps that you do in regression. So in sum, you first look for non-normality. Actually, you start with your hypothesis test and you look for normality, and we saw that there is a normality problem. And what we did, we actually went then right to running the regression, and actually we skipped one step, which is the correlation matrix. And sometimes, because all our variables, they were carrying the expected sign, That's always good. But sometimes you have a situation where you run a regression and suddenly the sign starts to flip. So let's say in a bivariate regression, you find that income inequality has a positive sign. But then in a multivariate regression with more independent variables, it suddenly becomes non-significant or even flips the sign and might be significant. So that is a problem that can often be traced to multicollinearity. And multicollinearity occurs whenever the right-hand side variables, the independent variables, go in the very same direction and have a strong correlation among themselves. So we skipped that step. But I still want to show it to you. So if we want to see whether our variables are strongly correlated with each other, we can actually show a correlation matrix. At least I hope so, that this is available here in Excel, data analysis. And then let's see, there is correlation. Okay. Input range, again, labels in first row. Yeah. And our observations are grouped in columns. And again, I want it as a new worksheet ply or sheet. So we just highlight LNY, LN GPI, LN Gini, infant mortality. And then let's take a look at a correlation matrix. And you see that actually infant mortality and GDP per capita, they have a strong relationship. But of course, one is the dependent and the other the independent variable. So we have to really focus on what's happening among the independent variable. So on the right-hand side, we have GDP and LNY, and LNY is most strongly correlated with infant mortality, but actually not so much with the gender parity index or the Gini. As a rule of thumb, whenever your correlation coefficient is greater than 0.6, you have a strong relationship. Whenever it is above 0.3 in absolute terms, it is medium. So the 0.33 is even at a very low end. So GDP per capita and GPI and LN Gini don't really correlate highly. And also the Gini coefficient and GPI, that does not correlate highly either. So from the perspective of multicollinearity destroying our model or creating some unexpected sign or flipping signs is not really an issue when looking at a correlation matrix. So again, the steps in running a regression is build your theory, check the variables for normality, and introduce log transformation whenever possible. Log transformations only work when your data is skewed to the right. If it is skewed to the left, there's not really much you can do typically. Or you have to do a transformation that makes the data very complicated or very difficult to interpret. But anyhow, any good regression model can tolerate a few non-normally distributed variables. What matters is that the residuals are normally distributed, and that makes it a good model. So step 2, control for nonlinearity. Step 3, which we actually omitted here, and I just showed it to you at the end. Take a look at the correlation matrix just to be alert for possible opposite signs or non-significant signs. Whenever you have a strong theory that's not corroborated by your results, multicollinearity is often a concern. The next step is that you actually run your regression and a little bit hope for the best. And if everything looks good, as it did in our case, the last step is to look still at the residuals, and if they also look nicely distributed, then you have a pretty solid model. Again, there's so much more you can do with regression, but that was just like a first overview. Hopefully that created some appetite for doing, more research on your own. But yeah, that pretty much concludes the lecture on regression, and I hope that you got the basic idea and saw the basic picture and feel comfortable enough to maybe work with your own data and run your own regressions. All right, so yeah, thanks a lot.